the silence is absolute. Not the quiet of a library or the hush of a cathedral, but the complete absence of everything. No air to carry sound, no space for vibrations to travel, no time for moments to unfold. This is the void that supposedly preceded our universe, a nothingness so profound that even the concept of preceding becomes meaningless. Yet in laboratories across the world, scientists are daring to ask the impossible question: what existed before the Big Bang? The question seems absurd on its face. How can there be a before when time itself allegedly began with that cosmic expansion 13.8 billion years ago? It's like asking what's north of the North Pole or what colour is the sound of silence. The very grammar of the inquiry appears to collapse under its own logical weight. Yet this linguistic impossibility has become one of the most urgent frontiers in modern physics, driving researchers to peer beyond the supposed beginning of everything. In the pristine corridors of Princeton University's physics department, where Albert Einstein once pondered the mysteries of space-time, contemporary physicists grapple with equations that refuse to respect the boundaries of conventional wisdom. Their blackboards are covered not with simple calculations, but with mathematical expressions that stretch the very meaning of existence, formulas that dare to describe states of being that preceded being itself. The quest began innocuously enough. Throughout the 20th century, astronomers gradually pieced together the story of cosmic expansion. Edwin Hubble's observations in the 1920s revealed that distant galaxies were racing away from us, their light stretched red by the expansion of space itself. Working backward through this cosmic film reel, scientists reached an inevitable conclusion. If everything was expanding now, then everything must have been compressed into a single point in the distant past. This moment of infinite density and temperature received the dismissive nickname Big Bang from astronomer Fred Hoyle in 1949, a term he coined to mock the very theory that would ultimately bear his skeptical label. Hoyle himself favoured a steady-state universe, eternal and unchanging, but the evidence kept mounting. The discovery of cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson provided the smoking gun, a faint afterglow still permeating space, the last echo of that primordial moment. Yet even as the Big Bang theory achieved scientific consensus, a troubling realization emerged. The mathematics that described this cosmic beginning also marked the absolute boundary of scientific knowledge. At the moment of the Big Bang itself, technically at the Planck time of 10 to the negative 43rd seconds after the expansion began, the equations that govern reality simply broke down. Temperature and density soared to infinity. Space-time itself became meaningless. It was as if the universe came with a factory-installed firewall, permanently concealing its own origins. For decades, physicists accepted this limitation with a mixture of frustration and resignation. The Big Bang represented the ultimate scientific horizon, the point beyond which knowledge could not venture. Asking what came before was relegated to philosophy or theology, banished from the realm of empirical inquiry. The universe, it seemed, had erected an impenetrable wall around its own birth certificate. But science has never been comfortable with absolute boundaries. In the 1980s, a new generation of cosmologists began to chip away at this cosmic censorship. Alan Guth, working late nights at Stanford's Linear Accelerator Center, stumbled upon a radical insight that would crack open the door to the pre-Big Bang era. His theory of cosmic inflation proposed that the universe underwent a period of exponential expansion in its earliest moments, not the gentle expansion we observe today, but a violent stretching that doubled the size of space every 10 to the negative 35th seconds. Inflation solved several nagging problems with the standard Big Bang model. It explained why the universe appears so uniform in all directions, why space seems geometrically flat, and why certain predicted particles have never been observed. But inflation also introduced a revolutionary concept. If the universe inflated dramatically in its earliest moments, then the Big Bang we thought marked the beginning might actually be the end of something else, the conclusion of a pre-existing inflationary phase. The implications were staggering. Rather than emerging from nothing, our universe might be the latest chapter in a much older story. The Big Bang, that supposed moment of creation, could instead mark a transition, the point where a pre-existing realm gave birth to the space-time we inhabit. Suddenly, the question of before was no longer meaningless, it was urgent. This revelation opened floodgates of theoretical speculation. If there was a before, what did it look like? Was it another universe, slowly dying as ours was born? Was it a higher dimensional realm where different laws of physics held sway? Or was it something so alien to our experience that we lack even the conceptual vocabulary to describe it? Andrei Lin, working at Moscow's Lebedev Institute before later joining Stanford, pushed the concept even further. His theory of eternal inflation suggested that inflation might be an ongoing process, constantly creating new bubble universes within an ever-expanding cosmic foam. In this scenario, our Big Bang was just one of countless similar events, each spawning a new pocket of space-time within an eternal, inflating multiverse. Meanwhile, string theorists proposed that our three-dimensional universe might be embedded within higher dimensional spaces called branes. When these branes collided, they theorized the tremendous energy release could trigger the birth of new universes. The Big Bang in this model was the echo of a cosmic collision that occurred in dimensions we cannot directly perceive. Each theory opened new possibilities while raising deeper questions. If our universe emerged from a pre-existing state, what governed that state? What physical laws operated in a realm before space and time as we know them? And most tantalizingly, might there be observable evidence, fossilized traces within our own universe, that could reveal the nature of this mysterious before? And the search for such evidence has become one of the most sophisticated detective stories in science. Researchers scrutinize the cosmic microwave background radiation with unprecedented precision, looking for subtle patterns that might preserve memories of pre-Big Bang physics. They study the distribution of galaxies across vast distances, seeking signatures of processes that occurred before our universe properly began. They probe the quantum vacuum itself, investigating whether the apparent nothingness of empty space might hold clues to what preceded everything. What they are discovering challenges our most fundamental assumptions about reality. The boundary between existence and non-existence, between something and nothing, appears far more porous than anyone imagined. The universe we inhabit may be just the visible tip of an iceberg whose bulk exists in realms we're only beginning to glimpse. As we stand on the threshold of potentially answering the most profound question humans have ever asked, we must first confront a troubling realization. Everything we thought we knew about beginnings may be wrong. The Big Bang, that definitive moment of cosmic genesis, may be neither big nor the beginning we imagined. But to understand what may have existed before everything, we must first confront what the Big Bang actually was and wasn't. The explosion never happened. This fundamental misconception has plagued public understanding of cosmic origins for over 70 years, painting a picture of primordial detonation that bears no resemblance to the actual physics involved. The Big Bang was not a bomb going off in empty space, scattering matter like cosmic shrapnel. It was something far more profound and alien. The expansion of space itself, carrying everything within it on a journey that defies human intuition. In the basement laboratories of Bell Telephone Laboratories in Holmdel, New Jersey, during the summer of 1965, two radio astronomers were struggling with a persistent hiss in their antenna. Arno Penzias and Robert Wilson had been tasked with eliminating all sources of interference from their precision instrument, designed to receive signals bounced off communication satellites. They cleaned pigeon droppings from the horn-shaped receiver, checked every electrical connection, and even briefly considered whether atmospheric nuclear testing might be contaminating their readings. What they discovered instead was the afterglow of creation itself, a faint whisper of microwave radiation coming from every direction in the sky, with almost perfect uniformity. The temperature of this cosmic background radiation was precisely what theoretical physicists had predicted for the cooled remnant of a universe that began in an extremely hot, dense state. The discovery earned them the Nobel Prize and provided the most compelling evidence that our universe had indeed emerged from a radically different condition billions of years ago. But the cosmic microwave background revealed something troubling about the standard Big Bang model. The radiation was too uniform, too perfectly smooth across vast regions of space that should never have been in contact with each other. If the universe had expanded at a steady rate since its beginning, opposite sides of the observable cosmos would have been separated by distances so vast that light itself could never have travelled between them. Yet these causally disconnected regions showed identical temperatures to within 1 part in 100,000. This became known as the horizon problem, and it suggested that our understanding of cosmic beginnings was fundamentally incomplete. How could distant regions of space share the same temperature if they had never been able to exchange information? It was as if two people living on opposite sides of an isolated island somehow ended up wearing identical clothing without ever meeting or communicating. The problem deepened when astronomers measured the geometry of space itself. According to Einstein's general relativity, the curvature of space-time depends on the total amount of matter and energy it contains. Too little, and space curves inward like the surface of a sphere. Too much, and it curves outward like a saddle. But observations revealed that our universe exists precisely at the critical boundary between these extremes. Space is geometrically flat to within extraordinary precision. This flatness presented another puzzle. In the standard Big Bang model, maintaining flat geometry required the universe to begin with exactly the right amount of matter and energy, balanced to within 1 part in 10 to the 60th power. Such precision seemed to require impossibly fine-tuned initial conditions, as if someone had carefully adjusted cosmic parameters to 15 decimal places before starting the expansion. A third problem emerged from particle physics. Grand-unified theories predicted that the extreme temperatures of the early universe should have produced exotic particles called magnetic monopoles, objects carrying isolated north or south magnetic poles, unlike ordinary magnets which always have both. These monopoles should be abundant in the observable universe, yet despite decades of searching, none had ever been detected. By the late 1970s, these problems, horizon, flatness, and monopole, cast serious doubt on the standard Big Bang picture. The theory explained cosmic expansion and the microwave background beautifully, but it required a set of initial conditions so specific and improbable that many physicists began searching for alternatives. The solution came from an unexpected quarter: the marriage of cosmology with particle physics. Alan Guth, a postdoctoral researcher at Stanford Linear Accelerator Center, was investigating phase transitions in the early universe, moments when the fundamental forces of nature separated from a unified state as temperatures dropped. Working late into the night on December 15, 1979, he discovered that certain phase transitions could trigger a period of exponential expansion, far more violent than anything in the standard model. Guth called this process cosmic inflation, and its implications were revolutionary. During the inflationary epoch, space itself stretched at an extraordinary rate, doubling in size approximately every 10 to the negative 34th power seconds. In less than the time it takes light to cross a proton, a region smaller than a subatomic particle expanded to the size of a grapefruit. This explosive growth continued for a tiny fraction of a second before inflation ended and the universe settled into the gentler expansion we observe today. Inflation solved the 3 major problems plaguing Big Bang cosmology with elegant simplicity. The horizon problem disappeared because regions that appear causally disconnected today were actually in close contact before inflation began. They shared the same temperature when they were squeezed together in a microscopic volume, then were stretched apart during the inflationary expansion. The flatness problem evaporated because inflation naturally drove space toward perfect geometric flatness, regardless of its initial curvature. And the monopole problem vanished because inflation diluted these exotic particles to undetectable levels, spreading them so thinly throughout the expanded universe that we would never expect to encounter one. But inflation introduced a conceptual revolution that extended far beyond solving technical problems. If the observable universe emerged from a microscopic patch that underwent exponential expansion, then the Big Bang was not really the beginning of everything, it was the end of inflation. The violent expansion we call cosmic creation might actually mark the transition between 2 distinct phases of cosmic evolution, an inflationary epoch we could barely imagine, and the radiation-dominated era that eventually produced stars, galaxies, and life. This realization fundamentally altered the meaning of cosmic origins. Rather than emerging from a singular moment of creation, our universe might be the product of pre-existing physics operating in a realm beyond direct observation. The Big Bang became not a beginning, but a boundary, the point where one cosmic epoch ended and another began. Andrei Linde, working first in Moscow and later at Stanford, pushed this insight even further. His models of chaotic inflation suggested that the inflationary process might be eternal, continuously creating new regions of space that undergo their own exponential expansion. In this scenario, inflation never completely ends. It continues forever in some regions while ending in others, creating an infinite hierarchy of bubble universes within an ever-expanding cosmic foam. Each bubble universe would experience its own Big Bang, when inflation ended in that particular region, but the larger inflationary process would continue indefinitely. Our observable universe would be just one bubble among countless others, each with potentially different physical constants, particle types, and even spatial dimensions. The Big Bang that created our cosmic home would be a local event within a much grander, possibly eternal process. These insights forced physicists to reconsider the most basic assumptions about cosmic beginnings. If inflation preceded our Big Bang, then asking about the universe's origin required understanding the conditions that triggered inflation itself. What caused space to begin expanding exponentially in the first place? What determined when and where inflation would end? And most provocatively, what existed before inflation began? The questions multiplied as theoretical models grew more sophisticated. String theory suggested that our three-dimensional universe might be embedded within higher dimensional spaces, with cosmic expansion triggered by collisions between these higher dimensional objects called branes. Loop quantum gravity proposed that space-time itself might be quantized, made up of discrete units rather than forming a smooth continuum, with the Big Bang representing a quantum bounce from a previous collapsing phase. Each theoretical framework offered different perspectives on pre-Big Bang physics, but they all shared a common theme. The expansion we observe today might be just the latest chapter in a much longer cosmic story. The universe we inhabit, with its familiar three dimensions of space and one dimension of time, might be the product of processes operating in realms governed by radically different physics. Modern observations have begun to test these ideas with unprecedented precision. The Planck satellite launched by the European Space Agency mapped the cosmic microwave background with such accuracy that subtle deviations from perfect uniformity became visible for the first time. These tiny fluctuations, predicted by inflationary theory, represent the quantum mechanical seeds from which all cosmic structure eventually grew. Galaxies, stars, and planets can trace their origins to microscopic variations in the density of primordial space. But the same observations that confirmed inflation also revealed new mysteries. The microwave background contains anomalies, large-scale patterns that don't match the predictions of the simplest inflationary models. Some of these features might represent signatures of the pre-inflationary universe, fossilized imprints of whatever conditions existed before our cosmic expansion began. The discovery of gravitational waves by the LIGO collaboration opened another window into the early universe. These ripples in space-time itself, created by colliding black holes and neutron stars, demonstrated that space is indeed dynamic and capable of carrying information across cosmic distances. Future gravitational wave detectors might detect primordial waves generated during inflation, providing direct evidence of the universe's exponential expansion phase. As our observational capabilities advance, the boundary between speculation and testable science continues to shift. Questions that seemed forever beyond empirical investigation are becoming subjects of observational cosmology. The pre-Big Bang universe, once relegated to philosophical speculation, is emerging as a legitimate frontier for scientific inquiry. Yet each answer only deepens the mystery. If our universe emerged from inflation, what triggered that inflationary epoch? If inflation itself had a beginning, what preceded it? The recursive nature of these questions suggests that cosmic origins might involve an infinite regress, with each apparent beginning revealing itself as the continuation of something even more fundamental. The implications extend beyond abstract physics into the realm of human meaning and purpose. If our universe is one bubble among countless others in an eternal inflationary multiverse, what does that mean for our significance in the cosmic order? If the Big Bang was not a unique moment of creation but merely one transition among many, how do we understand our place in this vast, possibly infinite hierarchy of cosmic evolution? These questions drive us deeper into the heart of the mystery, toward realms where our most fundamental concepts, time, space, causation, existence itself begin to lose their familiar meanings. To understand what may have preceded our cosmic origins, we must first confront the ultimate barrier to knowledge, the moment when physics itself breaks down and mathematics dissolves into meaninglessness. The equations screamed at 10 to the negative 43rd power seconds. At this precise moment after the Big Bang, a duration so brief that light could travel only 1/10,000,000th the width of a proton, the mathematical foundations of physics collapsed into incoherent infinities. Temperature soared beyond measure. Density crushed matter into meaningless abstraction. The very concepts of distance and duration dissolved into quantum foam. This was the Planck wall, the ultimate barrier between knowledge and mystery, where the two pillars of modern physics, quantum mechanics and general relativity, met in catastrophic contradiction. Max Planck never intended to erect a wall around cosmic origins when he introduced his fundamental constants in 1900. The German physicist was simply trying to understand blackbody radiation, the glow emitted by heated objects. His solution required a new fundamental constant, now called Planck's constant, that defined the smallest possible unit of energy exchange in quantum interactions. But when combined with other fundamental constants like the speed of light and Newton's gravitational constant, Planck's discovery revealed natural units of measurement that appeared to represent the absolute limits of meaningful physics. The Planck length emerged as approximately 10 to the negative 35th power meters, a distance so small that measuring anything shorter becomes impossible in principle, not just in practice. The Planck time, 10 to the negative 43rd power seconds, represents the smallest meaningful interval of time. At scales shorter than these Planck units, the smooth fabric of space-time described by Einstein's relativity dissolves into quantum uncertainty, where the very notion of precise position and timing becomes meaningless. John Wheeler, the Princeton physicist who coined the term black hole, described this realm as quantum foam, a seething, probabilistic landscape where virtual particles bubble in and out of existence, where space itself fluctuates wildly between different possible geometries. At the Planck scale, reality becomes fundamentally granular rather than continuous, more like a choppy sea than the smooth ocean surface we observe at larger scales. This posed an insurmountable problem for understanding cosmic origins. As cosmologists traced the Big Bang backward in time, approaching closer and closer to the initial moment, they inevitably reached the Planck epoch, the first 10 to the negative 43rd power seconds of cosmic history. Beyond this point, the equations that successfully described the expanding universe simply broke down. General relativity, which had precisely predicted cosmic expansion and gravitational waves, produced meaningless infinities. Quantum field theory, which had accurately described particle interactions, became unable to define consistent probabilities. The breakdown wasn't merely a technical limitation that better mathematics might eventually overcome. It represented a fundamental crisis in our understanding of reality. At the Planck scale, quantum mechanics insisted that energy and matter existed in discrete packets, while general relativity demanded smooth, continuous curvature of space-time. Quantum theory required precise knowledge of particle positions and momenta, while relativity showed that such precision was impossible near extreme gravitational fields. The two theories weren't just incompatible, they were actively contradictory. Stephen Hawking, working at Cambridge University in the 1970s, demonstrated just how profound this contradiction could become. His investigation of black hole physics revealed that these collapsed stars possessed temperatures and entropy, suggesting they could evaporate through quantum radiation. But when Hawking applied quantum field theory to curved spacetime near black holes, he discovered that information seemed to disappear completely when black holes evaporated, violating one of the most fundamental principles of quantum mechanics. The black hole information paradox became a microcosm of the larger crisis facing physics at the Planck scale. If quantum mechanics and general relativity couldn't coexist peacefully around black holes, how could they describe the conditions at cosmic origins, where densities exceeded those of any black hole by unimaginable factors? The singularity at the heart of Big Bang cosmology represented this crisis in its starkest form. According to general relativity, the universe began from a state of infinite density and infinite temperature, a mathematical point containing all the mass and energy that would eventually populate billions of galaxies. But infinite densities and temperatures weren't just impossible to achieve physically. They rendered the equations of physics meaningless. Division by zero appeared everywhere. Physical quantities became undefined. The theory that had successfully predicted cosmic expansion ultimately predicted its own failure. Many physicists suspected that these infinities were mathematical artifacts rather than physical realities. Just as the divergent series that plagued early quantum field theory were eventually resolved through renormalization techniques, perhaps the singularity problem would yield to more sophisticated theoretical approaches. But decades of effort had failed to produce a consistent quantum theory of gravity that could describe physics at the Planck scale. Roger Penrose, working at Oxford University, took a different approach to the singularity problem. Rather than viewing infinite densities as mathematical errors, he investigated whether singularities might be inevitable consequences of gravitational collapse. His singularity theorems, developed with Hawking in the 1960s, proved that under very general conditions, the equations of general relativity necessarily led to points where curvature became infinite and physics broke down. These theorems applied not only to black holes but to cosmic origins as well. If the universe was currently expanding and filled with ordinary matter, then running time backward inevitably led to a moment when all matter and energy occupied zero volume, a true physical singularity, not merely a mathematical inconvenience. The theorem seemed to prove that the Big Bang singularity was unavoidable within the framework of classical general relativity. But the singularity theorems also contained a crucial assumption. They applied to classical physics, ignoring quantum effects. As conditions approached the Planck scale, quantum mechanics necessarily became important, potentially preventing the formation of true singularities. The question was whether quantum gravity effects would merely smooth out the singularity into something finite but still extreme, or whether they might eliminate the Big Bang altogether, replacing it with something more exotic. Attempts to develop quantum theories of gravity proliferated throughout the late 20th century. String theory proposed that fundamental particles were not point-like objects, but tiny vibrating loops of energy, existing in 10 or 11 dimensions rather than the familiar 4. Loop quantum gravity suggested that space itself was quantized, composed of discrete units analogous to atoms of volume. Causal dynamical triangulation attempted to build spacetime from simple geometric pieces, like cosmic Lego blocks assembled according to quantum rules. Each approach offered different perspectives on what might happen at the Planck scale, but none provided definitive answers about cosmic origins. String theory required additional dimensions that remained hidden from direct observation. Loop quantum gravity made specific predictions about the quantization of area and volume, but these effects only became apparent at scales far too small to measure with current technology. The mathematical complexity of these theories often exceeded human ability to extract clear physical predictions. Meanwhile, observational cosmology was pushing closer to the Planck epoch through increasingly precise measurements. The Cosmic Background Explorer satellite, launched in 1989, mapped the temperature variations in the cosmic microwave background with unprecedented accuracy, revealing the tiny fluctuations that would eventually grow into galaxies and galaxy clusters. These measurements pushed our empirical knowledge of the early universe back to approximately 380,000 years after the Big Bang Bang, still enormously far from the Planck epoch, but closer than ever before. The Wilkinson Microwave Anisotropy Probe, launched in 2001, refined these measurements further, determining cosmic parameters with percent-level precision. The Planck satellite, operational from 2009 to 2013, pushed observational cosmology to its theoretical limits, mapping temperature variations as small as a few parts per million across the entire sky. Each mission revealed new details about the early universe while emphasizing how much remained unknown about the first moments of cosmic history. The precision of these observations paradoxically deepened the mystery of cosmic origins. The tiny temperature variations observed in the microwave background matched the predictions of inflationary theory with remarkable accuracy, confirming that quantum fluctuations in the early universe had indeed grown into cosmic structure. But the observations also revealed anomalies, large-scale patterns that didn't quite match the simplest inflationary models. suggesting that unknown physics might have operated during the universe's earliest moments. Some of these anomalies appeared to violate statistical isotropy, showing preferred directions in the microwave background that shouldn't exist if inflation had completely erased all traces of pre-Big Bang conditions. Other features, such as an apparent suppression of temperature fluctuations on the largest angular scales, hinted at physics beyond the standard inflationary paradigm. These anomalies were subtle, requiring sophisticated statistical analysis to detect, but they raised the tantalizing possibility that observations might preserve fossilized evidence of pre-Big Bang physics. The cold spot, a region of the microwave background approximately 1 billion light-years across that appears significantly cooler than its surroundings, became one of the most intriguing anomalies. While most cosmologists attributed this feature to statistical fluctuations or foreground contamination, a minority proposed more exotic explanations. Some suggested it might represent a collision between our universe and another bubble universe during the inflationary epoch. Others speculated it could be evidence of non-trivial topology, a universe with unusual connectivity that would preserve traces of pre-Big Bang geometry. The axis of evil, a provocative name given to an apparent alignment of the larger scale temperature fluctuations with the plane of the solar system, presented another puzzle. This alignment seemed to violate the cosmological principle that the universe should appear isotropic on large scales. While most physicists attributed this correlation to systematic observational effects or cosmic coincidence, others wondered whether it might indicate that our local cosmic environment retained some memory of conditions that existed before inflation. As observational precision increased, the gulf between what we could measure and what we needed to know about cosmic origins became more apparent. The Planck epoch remained as inaccessible as ever, protected by the fundamental incompatibility between quantum mechanics and general relativity. But the accumulating evidence suggested that this barrier might not be impermeable. The silence before time was not empty. Hidden within the mathematical chaos of the Planck epoch, patterns began to emerge that suggested structure rather than mere randomness. Quantum fluctuations in the vacuum of space, once thought to be purely statistical phenomena, showed correlations that persisted across cosmic scales. The geometry of space-time itself, at dimensions where measurement became impossible, nevertheless left imprints that could be detected billions of years later. These hints pointed toward a radical possibility, that the Planck wall might be a horizon rather than a barrier, concealing a realm of physics that operated according to principles we had barely begun to imagine. The equations that broke down at 10 to the negative 43rd power seconds might not represent the end of physical law, but rather the boundary between familiar physics and something far stranger. The mathematical structures that emerged from string theory and loop quantum gravity suggested that space-time itself might not be fundamental. Just as temperature and pressure turned out to be emergent properties of molecular motion, space and time might arise from more basic quantum informational processes operating at scales below the Planck length. If space-time was emergent rather than fundamental, then the Big Bang might not represent the beginning of everything, but rather the moment when space-time crystallized out of a more primitive quantum substrate. This possibility opened extraordinary new questions about the nature of cosmic origins. If space-time emerged from something more fundamental, what governed that underlying realm? Did causation exist before time? Could information persist through the transition from pre-space-time to space-time? And most provocatively, might there be ways to detect evidence of this pre-geometric realm within our own universe? The search for answers was leading physicists into territories where the very concepts of before and after began to lose meaning, where cause and effect became entangled in quantum superposition, where the distinction between existence and non-existence blurred beyond recognition. At the edge of the Planck epoch, the familiar universe dissolved into something that defied not only measurement but comprehension. Yet patterns were emerging from this conceptual chaos, mathematical structures that hinted at profound new physics operating beyond the reach of direct observation. The silence before time was beginning to whisper its secrets to those bold enough to listen. In a small office at Princeton University during the winter of 1984, physicist Paul Steinhardt stared at a blackboard covered with the mathematical debris of failed attempts to understand cosmic origins. The standard Big Bang model lay in ruins, contradicted by its own implications. Inflation had solved some problems while creating others. The Planck wall seemed impenetrable. But what if, Steinhardt wondered, the universe had never had a beginning at all? This heretical thought launched a revolution in cosmological thinking that would challenge humanity's most basic assumptions about time, causation, and existence itself. Rather than seeking to peer beyond the Big Bang, a new generation of physicists began to question whether there had ever been a beyond to discover. Perhaps the universe was eternal, cycling through endless phases of expansion and contraction, with each apparent beginning simply marking the transition from one cosmic epoch to another. The cyclic universe represented more than just another theoretical model. It demanded a complete reconceptualization of cosmic evolution. In Steinhardt's vision, developed with Neil Turok at Cambridge University, our Big Bang was neither the beginning of time nor a unique event, but merely the latest in an infinite sequence of cosmic transitions. The universe expanded, slowed, stopped, contracted, and bounced back into a new phase of expansion, over and over for eternity. This cyclical model solves several of the deepest problems in cosmology with elegant simplicity. The horizon problem disappeared, because distant regions of space had been in contact during previous cosmic cycles, even if they appeared disconnected today. The flatness problem evaporated because each cycle naturally drove the geometry of space toward perfect flatness, regardless of initial conditions. Most remarkably, the model eliminated the need for fine-tuned initial conditions entirely, since the universe had no beginning that required special setup. But the cyclic model faced a fundamental challenge: entropy. The second law of thermodynamics demanded that each cycle should produce more disorder than the last, gradually filling the universe with black holes, waste heat, and other forms of irreversible decay. After countless cycles, the universe should have reached maximum entropy long ago, a state of perfect equilibrium where no further evolution was possible. Yet here we were, living in a universe filled with stars, galaxies, and complex structures that seemed far from thermodynamic equilibrium. The resolution came from an unexpected direction: higher dimensions. String theory, the ambitious attempt to unify quantum mechanics and general relativity, required our familiar 3 dimensions of space and 1 dimension of time to be embedded within a larger framework of 10 or 11 total dimensions. Most of these extra dimensions were presumed to be compactified, rolled up so small that they remained invisible at ordinary scales. But what if some remained large enough to influence cosmic evolution? Lisa Randall at Harvard University and Raman Sundram at Johns Hopkins developed models where our entire universe existed as a 3-dimensional membrane, or brain, floating within a higher dimensional space called the bulk. In their scenario, gravity could propagate through all dimensions of the bulk, while other forces remained confined to our brain. This explained why gravity appeared so much weaker than electromagnetic or nuclear forces. Most of its strength leaked away into dimensions we couldn't directly perceive. The brain-world models opened extraordinary new possibilities for cosmic origins. If our universe was a brain embedded in higher dimensions, then cosmic evolution might be driven by collisions between different brains floating through the bulk. When 2 brains collided, the tremendous energy release could heat both surfaces to enormous temperatures, creating conditions indistinguishable from the hot Big Bang we observed within our own cosmic history. Steinhardt and Turok seized on this insight to develop the ekpyrotic scenario, named after the ancient Stoic concept of cosmic conflagration and renewal. In their model, our universe existed as one brain among many, separated by small gaps in the higher dimensional bulk. Periodically, these brains would approach each other, collide, separate, and repeat the process in endless cycles. Each collision would appear from within our brain as a Big Bang, a moment of creation when space filled with hot, dense matter and radiation. The ekpyrotic model made specific predictions that distinguished it from both standard Big Bang cosmology and simple inflationary scenarios. Rather than producing gravitational waves with random polarizations, brain collisions should generate waves with distinctive patterns that could be detected by future generations of gravitational wave observatories. The model also predicted specific relationships between the amplitudes of density fluctuations at different scales, potentially observable in the cosmic microwave background. Meanwhile, other physicists were exploring radically different approaches to pre-Big Bang physics. Abhay Ashtekar at Pennsylvania State University pioneered loop quantum cosmology, applying the techniques of loop quantum gravity to cosmic evolution. In this approach, space itself was quantized into discrete units, like pixels in a cosmic image, with each unit containing a fixed quantum of volume. The quantization of space had profound implications for cosmic origins. As the universe contracted toward what would classically be a Big Bang singularity, quantum effects became important when the density approached the Planck scale. Rather than allowing infinite compression, the discrete structure of quantum space created a repulsive force that halted the collapse and drove the universe into a new phase of expansion. The Big Bang became a big bounce, with our expanding universe emerging from the collapse of a previous cosmic epoch. Loop quantum cosmology made precise predictions about this bounce process. The maximum density reached during the transition was finite and calculable, approximately 1% of the Planck density. The duration of the bounce phase lasted approximately 10 to the negative 43rd power seconds, during which the universe transitioned from contraction to expansion. Most remarkably, information about the pre-bounce universe could survive the transition, potentially leaving observable signatures in the cosmic microwave background. Martin Bojewald, working with Ashtekar, showed that loop quantum cosmology could resolve the classical singularity while preserving many features of standard Big Bang nucleosynthesis and cosmic microwave background formation. The model predicted that our universe should contain subtle correlations between opposite sides of the sky, regions that were causally connected in the pre-bounce phase, but became separated during the subsequent expansion. As these bouncing cosmologies gained theoretical sophistication, they began to make contact with observational data. The Planck satellite's precise measurements of the cosmic microwave background revealed anomalies that didn't quite match the predictions of simple inflationary models. Some of these features, such as the suppression of power at the largest angular scales, could potentially be explained by pre-Big Bang physics operating during a previous cosmic cycle. Roger Penrose, the Oxford mathematician who had proved that singularities were inevitable in classical general relativity, proposed yet another radical alternative to standard cosmic origins. His conformal cyclic cosmology suggested that the universe underwent infinite cycles of expansion, but with a twist that eliminated the entropy problem plaguing other cyclic models. Penrose's insight was that the far future of our universe, when all matter had been consumed by black holes and all black holes had evaporated through Hawking radiation, would contain only massless particles, photons and gravitons travelling at the speed of light. For such particles, the passage of time became meaningless, allowing the infinitely expanded future of one cosmic cycle to connect smoothly with the Big Bang of the next cycle through a mathematical transformation called conformal rescaling. In Penrose's model, each cycle began with perfect order and ended in maximum entropy, but the conformal transition reset the clock, allowing the next cycle to begin fresh. The universe was eternal in both directions, with no beginning or end, but each cycle contained a finite amount of time and evolution. Our Big Bang represented the conformal boundary between the entropic death of a previous universe and the ordered birth of our own. The conformal cyclic cosmology made testable predictions about the cosmic microwave background. Penrose argued that massive black holes from the previous cycle should leave circular imprints in the temperature map, Hawking points, where the final evaporation of primordial black holes created distinctive patterns that survived the conformal transition. Several research groups claim to have detected these circular patterns in Planck satellite data, though the statistical significance remained controversial. Eternal inflation, meanwhile, continued to evolve in directions that challenged conventional notions of cosmic uniqueness. André Linde's chaotic inflation suggested that the inflationary process was generic rather than special, occurring whenever scalar fields found themselves in appropriate configurations within the quantum vacuum. But if inflation was generic, it should be happening everywhere, all the time, creating an infinite number of bubble universes within an ever-expanding cosmic foam. Alexander Vilenkin at Tufts University developed this insight into a comprehensive theory of eternal inflation. In his model, inflation never completely stopped. It ended in some regions, creating bubble universes like our own, while continuing forever in others. The result was an infinite multiverse containing every possible type of universe, including infinite copies of our own cosmic history, with every possible variation. The multiverse raised profound questions about probability and meaning in cosmology. If every possible universe existed somewhere within the eternal inflationary foam, how could cosmologists make predictions about what we should observe? The anthropic principle, the idea that we necessarily find ourselves in a universe compatible with our existence, became a powerful tool for selecting which universes could contain observers, but it also seemed to drain physics of its predictive power. Sean Carroll at the California Institute of Technology developed arrow of time scenarios that combined eternal inflation with thermodynamic considerations. In his model, the multiverse contained regions of both high and low entropy, with observers necessarily finding themselves in low entropy regions where complex structures could form. The past direction was defined as the direction toward lower entropy, naturally explaining why we remember the past but not the future, even in an eternally existing multiverse. These competing models of pre-Big Bang physics, cyclic branes, quantum bounces, conformal cycles, eternal inflation, shared certain common themes while differing dramatically in their specific predictions. All suggested that our Big Bang was not unique, but rather one event among many in a larger cosmic context. All implied that time extended infinitely into the past, eliminating the need for a moment of creation, and all predicted that careful observations of our own universe might reveal traces of the physics that operated before our cosmic expansion began. The theoretical diversity reflected the profound challenges involved in understanding cosmic origins. Unlike other areas of physics, where experiments could test theories directly, pre-Big Bang cosmology operated at the boundaries of the observable universe, where only the most subtle observational signatures could provide evidence for or against competing models. Yet the models made sufficiently different predictions that future observations might distinguish between them. Gravitational wave detectors sensitive to primordial signals could reveal whether our Big Bang emerged from brane collisions, quantum bounces, or inflationary fluctuations. More precise measurements of the cosmic microwave background might detect the circular patterns predicted by conformal cyclic cosmology or the correlations expected from loop quantum bounces. The study of cosmic structure formation could test whether our universe contained the statistical properties expected from eternal inflationary multiverse or cyclic evolution. As observational cosmology pushed toward these ultimate tests, the theoretical landscape continued to evolve. New models emerged regularly, each offering different perspectives on what might have existed before our cosmic expansion began. Some proposed that consciousness itself played a fundamental role in cosmic evolution, with observer selection effects determining which branch of the quantum multiverse became real. Others suggested that information, rather than matter or energy, was the most fundamental constituent of reality, with our material universe emerging from purely computational processes operating in abstract mathematical spaces. The diversity of theoretical possibilities reflected both the richness of modern physics and the profound mystery of cosmic origins. Each model captured some aspect of the puzzle while leaving others unexplained. The cyclic models explained cosmic flatness and solved the horizon problem, but struggled with entropy increase and quantum corrections. Eternal inflation naturally produced the observed statistical properties of cosmic structure, but required fine-tuning of initial conditions in the larger multiverse. Loop quantum cosmology resolved the singularity problem through precise mathematical techniques, but made assumptions about quantum gravity that remained unproven. Perhaps most remarkably, all of these models suggested that the question, "What was the universe like before the Big Bang?" had meaningful answers, even if those answers challenged human intuition about time, causation, and existence. The silence before time was not empty, but filled with structures and processes that transcended ordinary space-time, while remaining accessible to mathematical analysis and potentially observational test. The veil concealing cosmic origins was beginning to thin, revealing glimpses of realms that operated according to principles barely imaginable to creatures evolved within a single bubble of space-time. These glimpses suggested that our cosmic home might be just one small part of a vastly larger and more complex reality, where Big Bangs occurred as commonly as waves breaking on an infinite shore. The evidence was hiding in plain sight, encoded in the oldest light in the universe. In a temperature-controlled laboratory at the European Space Agency's Mission Control Center, in Darmstadt, Germany, scientists huddled around computer screens displaying what appeared to be a mottled oval, a map of the entire cosmos as it existed just 380,000 years after the Big Bang. The Planck satellite had spent 4 years scanning the heavens, measuring the cosmic microwave background with unprecedented precision, and now its final data release was revealing patterns that shouldn't exist. The anomalies were subtle, deviations from perfect randomness that required sophisticated statistical analysis to detect. But their implications were staggering. According to the standard model of cosmology, the temperature variations in the cosmic microwave background should be completely random, showing no preferred directions or special patterns. Instead, the data revealed correlations, alignments, and structures that hinted at physics operating before the inflationary epoch supposedly erased all traces of pre-Big Bang conditions. Amir Hajian, working at the Canadian Institute for Theoretical Astrophysics, was among the first to recognize the significance of these patterns. His analysis of the Planck data revealed that the largest scale temperature fluctuations were not randomly distributed across the sky, but showed a mysterious alignment with the plane of the solar system. This axis of evil, as it had been provocatively named, violated the cosmological principle that the universe should appear identical in all directions. Even more intriguing were the circular patterns that Roger Penrose and his collaborator Vahe Gozardian claimed to identify in the microwave background data. These rings, slightly warmer or cooler than their surroundings, matched the predictions of conformal cyclic cosmology with remarkable precision. If confirmed, they would represent direct observational evidence of black hole evaporation in the previous cosmic cycle, witnesses to eternity preserved in the afterglow of our own Big Bang. The controversy surrounding these claimed detections illustrated the challenge of extracting pre-Big Bang signatures from observational data. Multiple research groups analysed the same Planck measurements, applying different statistical techniques and reaching contradictory conclusions. Some found compelling evidence for circular patterns, others attributed the same features to random chance or systematic observational effects. The debate raged in academic journals and conference presentations, with the ultimate truth remaining tantalizingly just beyond definitive proof. Meanwhile, in the deep underground chambers of the Laser Interferometer Gravitational Wave Observatory, or LIGO, physicists were opening an entirely new window into cosmic origins. The detection of gravitational waves from colliding black holes and neutron stars in 2015 confirmed Einstein's century-old prediction that space-time itself could carry information across the universe in the form of ripples propagating at the speed of light. But the gravitational waves detected by LIGO came from relatively recent cosmic events, black holes that formed and collided within the past few billion years. Far more interesting were the primordial gravitational waves that should have been generated during the universe's earliest moments, carrying information about physics at energy scales far beyond anything achievable in terrestrial experiments. These primordial waves, if they existed, would provide the most direct possible probe of pre-Big Bang physics. Unlike electromagnetic radiation, which could only travel freely after the cosmic microwave background was emitted, gravitational waves could propagate unimpeded from the very first moments of cosmic history. They represented time capsules from the Planck epoch, potentially carrying signatures of quantum bounces, brain collisions, or other exotic processes that preceded our Big Bang. The BISEP experiments at the South Pole, led by John Kovacs at Harvard University, searched for these primordial gravitational waves by looking for their distinctive polarization signatures in the cosmic microwave background. In 2014, the BICEP-2 team announced the detection of the B-mode polarization patterns that seemed to confirm the existence of primordial waves, providing the first direct evidence for cosmic inflation and potentially revealing the energy scale at which quantum gravity effects became important. The announcement made international headlines and seemed to mark a breakthrough in our understanding of cosmic origins. But the celebration proved premature. Further analysis revealed that the detected polarization patterns could be explained entirely by dust within our own galaxy, rather than primordial gravitational waves from the early universe. The true signature of pre-Big Bang physics remained hidden beneath layers of contaminating signals from more recent cosmic evolution. The setback illustrated the extraordinary observational challenges involved in detecting pre-Big Bang signatures. Any signal from the earliest moments of cosmic history had to survive billions of years of cosmic evolution, remaining coherent despite the formation of galaxies, stars, and all the complex astrophysical processes that filled the universe with electromagnetic and gravitational noise. It was like trying to hear a whisper from across a crowded stadium during a thunderstorm. Yet other lines of evidence were emerging from unexpected directions. Studies of cosmic structure formation revealed anomalies in the distribution of galaxies that might preserve information about pre-inflationary physics. The Sloan Digital Sky Survey, which mapped the positions of over 1 million galaxies across enormous volumes of space, discovered that the largest structures in the universe showed subtle patterns that didn't quite match the predictions of standard cosmological models. Antonio Riotto at the University of Geneva analysed these large-scale structure observations, looking for signatures of non-Gaussianity, deviations from the simple statistical patterns expected if cosmic structure grew from purely random initial conditions. His work suggested that the primordial fluctuations that seeded galaxy formation might have been influenced by interactions between multiple fields during the inflationary epoch, potentially preserving information about the pre-inflationary state. The search for pre-Big Bang physics also led cosmologists to investigate some of the most extreme objects in the observable universe. Supermassive black holes, containing millions or billions of solar masses, appeared to have formed remarkably early in cosmic history, within the first billion years after the Big Bang. The rapid growth of these monsters seemed to require initial seeds that were far more massive than could be produced by the first generation of stars. Some cosmologists speculated that these supermassive black hole seeds might be primordial objects, formed from density fluctuations that existed before inflation began. If so, their properties could provide indirect evidence of pre-Big Bang physics, preserving information about cosmic conditions that preceded our observable expansion. The study of dark matter offered another potential window into pre-Big Bang physics. This mysterious substance, which comprised approximately 25% of the universe's total mass energy, interacted only weakly with ordinary matter and electromagnetic radiation. Its properties seemed to require physics beyond the standard model of particle physics, possibly involving particles that were produced during the earliest moments of cosmic history. Lisa Randall and her collaborators investigated the possibility that dark matter might consist of particles that existed in higher dimensions, occasionally interacting with our three-dimensional brain through gravitational effects. If dark matter originated from brain collisions or other pre-Big Bang processes, its distribution throughout space might preserve signatures of the exotic physics that created it. The Euclid Space Telescope, launched by the European Space Agency in 2023, began mapping the distribution of dark matter across enormous volumes of space by observing its gravitational effects on visible galaxies. The resulting three-dimensional maps revealed the cosmic web, a vast network of dark matter filaments connecting galaxy clusters across billions of light-years. Hidden within this web might be traces of the processes that operated before our Big Bang, fossilized in the pattern of invisible matter that comprised most of the universe. Quantum field theory and curved spacetime offered yet another approach to detecting pre-Big Bang signatures. The quantum vacuum, far from being empty space, seethes with virtual particles that appear and disappear according to the uncertainty principle. During the inflationary epoch, some of these quantum fluctuations were stretched to macroscopic scales, becoming the seeds of cosmic structure formation. But inflation might not have been the first process to stretch quantum fluctuations beyond the microscopic realm. If the universe underwent previous phases of expansion, during a quantum bounce, for example, or in earlier cycles of a cyclic cosmology, then some fluctuations might preserve information about multiple epochs of cosmic evolution. These palimpsest signatures would be extraordinarily difficult to detect, buried beneath layers of more recent cosmic history, but they might be recoverable through sufficiently sophisticated analysis techniques. Theoretical physicists developed increasingly creative methods for extracting pre-Big Bang information from observational data. Latham Boyle at the Perimeter Institute for Theoretical Physics proposed that the universe might have a mirror structure, with time running backward before the Big Bang and forward afterward. In this CPT symmetric model, the pre-Big Bang universe would appear as the time reverse of our post-Big Bang evolution, potentially leaving detectable signatures in the cosmic microwave background and other observational data. The holographic principle, emerging from black hole physics and string theory, suggested even more radical possibilities for preserving pre-Big Bang information. If our three-dimensional universe was actually encoded on a two-dimensional boundary, like a hologram projected from a flat surface, then information about pre-Big Bang physics might be stored in the quantum entanglement structure of this boundary. Leonard Susskind at Stanford University and Juan Maldacena at the Institute for Advanced Study developed these ideas into a comprehensive framework called the ADS-CFT correspondence, which described how gravity in higher dimensional spaces could be equivalent to quantum field theories on lower dimensional boundaries. While originally developed for theoretical models rather than realistic cosmologies, the holographic principle raised the possibility that all the information needed to reconstruct pre-Big Bang physics might already be encoded within our observable universe, waiting for the right mathematical tools to decode it. The search for these hidden signatures required new approaches that combined observational astronomy with theoretical physics in unprecedented ways. Machine learning algorithms trained on simulated cosmological data began identifying subtle patterns in observational surveys that human researchers had overlooked. Quantum information theory provided new tools for understanding how information could survive transitions between different cosmic epochs. Advanced statistical techniques borrowed from other fields, genetics, climate science, financial modeling, were adapted to extract weak signals from noisy cosmological data. Despite these methodological advances, the fundamental challenge remained unchanged. Any signal from pre-Big Bang physics had to be extracted from a background of cosmic evolution spanning nearly 14 billion years. It was like trying to identify the echo of a conversation that occurred in a room before it was demolished and rebuilt multiple times, with each reconstruction adding new layers of acoustic complexity. Yet the accumulating evidence suggested that such echoes might indeed be detectable. The anomalies in the cosmic microwave background, while individually inconclusive, formed a pattern that was difficult to explain through conventional post-Big Bang physics. The unexpected properties of primordial black holes, dark matter, and large-scale structure all hinted at physics operating during the universe's earliest moments. Most intriguingly, different types of observations seem to point towards similar conclusions about the exotic nature of cosmic origins. The James Webb Space Telescope, operational since 2022, added another layer of complexity to these investigations. Its infrared observations revealed the most distant galaxies ever detected, showing cosmic structure formation during the universe's first few 100 million years. These early galaxies appeared larger and more massive than theoretical models predicted, suggesting that structure formation began earlier and proceeded more rapidly than previously thought possible. Some cosmologists interpreted these observations as evidence for enhanced primordial fluctuations, density variations that were amplified by pre-inflationary physics before being processed by the standard inflationary mechanism. Others suggested that the early formation of massive structures required exotic dark matter models or modifications to general relativity that operated during the universe's earliest epochs. The European Southern Observatory's extremely large telescope, currently under construction, promised even more precise observations of the early universe. Its unprecedented light-gathering power would allow astronomers to study individual stars in the most distant galaxies, potentially revealing signatures of primordial nucleosynthesis processes that occurred during or immediately after the Big Bang transition. These next-generation observations would provide increasingly stringent tests of pre-Big Bang cosmological models. Cyclic scenarios made specific predictions about the statistical properties of primordial fluctuations. Eternal inflation implied particular relationships between cosmic parameters in different regions of space. Loop quantum cosmology predicted distinctive correlations in the cosmic microwave background that should be detectable with sufficient precision. As observational capabilities continued to advance, the boundary between speculation and testable science was shifting rapidly. Questions that had seemed forever beyond empirical investigation were becoming subjects of precision measurement. The pre-Big Bang universe, once relegated to philosophical discussion, was emerging as a legitimate target for scientific inquiry. The witnesses to eternity were speaking, their voices preserved in the cosmic microwave background, the distribution of dark matter, the pattern of galaxy formation, and the quantum structure of space itself. The challenge was learning to hear their testimony above the noise of cosmic evolution, extracting the signal of pre-Big Bang physics from the overwhelming background of more recent astronomical processes. But the patterns were there, waiting to be decoded by researchers bold enough to look beyond the supposed beginning of time itself. The pattern was unmistakable once you learned to see it. Across 13.8 billion years of cosmic history, the universe had written the same story over and over again. Birth, growth, complexity, decay, death, and then, somehow, renewal. From the quantum foam of the Planck epoch to the heat death predicted by thermodynamics, from the collapse of individual stars to the potential Big Bang rip that might tear apart space-time itself, cycles of destruction and creation appeared to be woven into the fundamental fabric of reality. This recognition dawned slowly on cosmologists as they pieced together the full scope of cosmic evolution. The universe was not simply expanding toward some final state of equilibrium, as had been assumed for most of the 20th century. Instead, it seemed to be following patterns that recurred across vastly different scales of space and time, suggesting that the cycle of cosmic death and rebirth might be as eternal as the mathematics that described it. Consider the life cycle of a single star. Born from the gravitational collapse of a molecular cloud, it ignited nuclear fusion in its core, converting hydrogen into helium while radiating energy that could sustain planetary systems for billions of years. But eventually the nuclear fuel was exhausted. For stars like our Sun, the end came as a gentle expansion into a red giant, followed by the shedding of outer layers and collapse into a white dwarf, a dense remnant that would cool slowly for trillions of years. More massive stars met more violent ends. When their cores could no longer sustain fusion, gravity overwhelmed nuclear forces in a catastrophic implosion lasting mere seconds. The resulting supernova explosions scattered heavy elements across interstellar space, while leaving behind either a neutron star, matter compressed to nuclear density, or a black hole where space-time curvature became so extreme that nothing, not even light, could escape. Yet even these cosmic catastrophes were acts of creation as well as destruction. The heavy elements forged in stellar cores and dispersed by supernovae became the raw materials for new generations of stars and planets. The shock waves from stellar explosions compressed nearby gas clouds, triggering fresh episodes of star formation. The universe recycled its contents continuously, with each stellar death enabling new births in an endless cosmic metabolism. This pattern of cyclic renewal operated on larger scales as well. Galaxies, those vast collections of hundreds of billions of stars, underwent their own processes of evolution and transformation. They collided and merged, feeding the supermassive black holes at their centers, while triggering bursts of new star formation. Galaxy clusters, the largest gravitationally bound structures in the universe, grew through the accretion of smaller systems while gradually losing their member galaxies to the accelerating expansion of space itself. Even black holes, those ultimate endpoints of gravitational collapse, were not permanent fixtures of the cosmic landscape. Stephen Hawking's discovery of black hole evaporation revealed that even these objects had finite lifetimes, slowly radiating away their mass through quantum effects at their event horizons. The largest black holes would take times incomparably longer than the current age of the universe to evaporate completely, but given sufficient time, they too would return their contents to the quantum vacuum from which they emerged. The implications became staggering when cosmologists extrapolated these cycles to the universe as a whole. If individual objects within the cosmos underwent endless transformations between different states, why should the cosmos itself be exempt from similar processes? The Big Bang, rather than representing a unique moment of creation, might be just one phase in an eternal cycle of cosmic death and rebirth. Freeman Dyson at the Institute for Advanced Study had explored the far future of cosmic evolution in a seminal 1979 paper that read more like science fiction than theoretical physics. He envisioned a universe expanding forever, growing colder and more dilute as the accelerating expansion separated matter across ever-increasing distances. Stars would cease forming as gas became too diffuse to collapse gravitationally. Existing stars would exhaust their nuclear fuel and fade into darkness. Protons themselves might decay, given sufficient time, dissolving even atomic nuclei into elementary particles and radiation. Yet even in this apparently terminal scenario, Dyson identified possibilities for renewal. Quantum fluctuations in the vacuum might occasionally produce matter from nothing, given the infinite time available in an eternally expanding universe. Random thermal motions could spontaneously organize into complex structures, including, with vanishingly small but non-zero probability, entire planetary systems or even living organisms. The universe might experience resurrection through pure chance, with all possible configurations eventually emerging from quantum noise. Roger Penrose pushed these ideas toward their logical extreme in his conformal cyclic cosmology. If the far future of our universe contained only massless particles, photons and gravitons travelling at the speed of light, then the concepts of distance and duration would become meaningless for these particles. This allowed Penrose to connect the infinitely expanded future of one cosmic cycle directly to the Big Bang beginning of the next cycle through a mathematical transformation that preserved the essential physics while resetting the cosmic clock. In Penrose's vision, our Big Bang represented not the creation of the universe from nothing, but rather the conformal boundary between the heat-death of a previous cosmic cycle and the ordered beginning of our own. The entropy that accumulated during one cycle was somehow reset or transformed during the transition, allowing the next cycle to begin with the low entropy conditions necessary for complex structure formation. The model made specific predictions about observable signatures in our current universe. The final moments of black hole evaporation in the previous cycle should have left circular patterns in the cosmic microwave background, Hawking points where the last gasps of primordial black holes created distinctive temperature and polarization signatures. Multiple research groups claim to have detected these patterns in satellite data, though the results remained controversial and disputed by other teams using different analysis techniques. Meanwhile, the discovery of cosmic acceleration in 1998 by the Supernova Cosmology Project and the High Z Supernova Search Team had introduced dark energy as a new player in cosmic evolution. This mysterious component, comprising approximately 70% of the universe's total energy density, was driving space to expand at an ever-increasing rate. Unlike matter and radiation, which became more dilute as space expanded, dark energy maintained constant density, providing an inexhaustible source of repulsive force. The implications of eternal cosmic acceleration were profound and disturbing. If dark energy continued to dominate cosmic evolution, the expansion of space would accelerate until it tore apart all gravitationally bound structures. First, galaxy clusters would dissolve as their member galaxies were carried beyond each other's gravitational reach. Then, individual galaxies would disintegrate as stars were separated by ever-increasing distances. Eventually, even atoms might be ripped apart if the acceleration continued to strengthen, a scenario cosmologists grimly dubbed the Big Rip. Yet some theoretical models suggested that dark energy might not remain constant forever. If it was associated with a scalar field similar to the inflaton that drove cosmic inflation, it might undergo phase transitions that dramatically altered its properties. The field could decay into ordinary matter and radiation, potentially triggering a new Big Bang within regions of space where the transition occurred. Our universe might be riddled with invisible domain walls where different vacuum states met, with new universes constantly bubbling into existence at the boundaries. Eternal inflation, developed by Andrei Linde and Alexander Vilenkin, provided the most comprehensive framework for understanding these cosmic recycling processes. In their models, inflation never completely ended but continued forever in some regions while terminating in others. Each termination event created a bubble universe with its own Big Bang, while the larger inflationary process persisted in the surrounding space. The result was an infinite fractal multiverse, where Big Bangs occurred continuously across an ever-expanding cosmic foam. Every possible type of universe would exist somewhere within this structure, including infinite copies of our own cosmos with every conceivable variation in its history. The multiverse would contain universes where dinosaurs never went extinct, where different physical constants governed the behavior of matter and energy, where the number of spatial dimensions varied from place to place. This proliferation of possibilities raised profound questions about probability and meaning in cosmology. If every possible universe existed somewhere within the eternal multiverse, how could scientists make predictions about what we should observe? The anthropic principle, the observation that we necessarily find ourselves in a universe compatible with the existence of intelligent life became a powerful tool for selecting which regions of the multiverse could contain observers like ourselves. Brandon Carter, working at the Meudon Observatory near Paris, had first articulated the anthropic principle in 1973 as a response to apparent fine-tuning in the physical constants that govern cosmic evolution. The strength of gravity, the mass of the electron, the rate of cosmic expansion all appeared to be precisely calibrated to allow the formation of stars, planets, and ultimately life itself. Even small changes in these parameters would have prevented the emergence of complexity in the universe. Rather than interpreting this fine-tuning as evidence for intelligent design, Carter suggested that it reflected selection effects operating within a larger ensemble of universes with different properties. We necessarily found ourselves in a universe where the constants allowed for our existence, regardless of how improbable such a universe might be within the full ensemble. The anthropic principle gained new significance in the context of eternal inflation and other multiverse models. If different regions of space contained different values of the physical constants, then most regions would be sterile, unable to support the complex chemistry necessary for life. But observers could only exist in the rare regions where conditions happened to be suitable, creating a selection bias that explained the apparent fine-tuning of our cosmic environment. Leonard Susskind at Stanford University developed these ideas into a comprehensive framework called the anthropic landscape. String theory, he argued, contained an enormous number of possible vacuum states, perhaps 10 to the 500 power different configurations, each corresponding to a different set of physical laws and constants. Eternal inflation would populate all of these possibilities somewhere within the multiverse, creating a vast landscape of universes with every conceivable combination of physical properties. Most of this landscape would be uninhabitable, consisting of universes where matter couldn't form stable structures or where the vacuum itself was unstable. But scattered throughout the landscape would be rare oases where conditions allowed for complexity, chemistry, and ultimately consciousness. These anthropically selected regions would appear fine-tuned to their inhabitants, even though they represented an infinitesimal fraction of the total multiverse. The anthropic landscape provided elegant solutions to several cosmological puzzles, but at the cost of abandoning traditional notions of scientific prediction. If the observed properties of our universe reflected anthropic selection rather than fundamental physical principles, then cosmology might be reduced to environmental biology, the study of which cosmic habitats could support different types of observers. Max Tegmark at MIT pushed these ideas toward their ultimate conclusion in his mathematical universe hypothesis. If eternal inflation could produce universes with every possible set of physical constants, why not universes with every possible mathematical structure? Perhaps every self-consistent mathematical system corresponded to a real universe somewhere within the ultimate multiverse, with our cosmos representing just one possible way of organizing abstract mathematical relationships. In Tegmark's vision, the question of what existed before the Big Bang became meaningless because mathematical structures were timeless. Our universe, with its particular history of cosmic expansion and evolution, was simply one eternal mathematical object among infinitely many others. The Big Bang was not an event that occurred at a particular time, but rather a boundary condition built into the mathematical structure that defined our cosmic reality. These speculative possibilities challenge the most basic assumptions about scientific methodology and cosmic purpose. If every possible universe existed eternally within some ultimate multiverse, what distinguished real physics from mathematical fantasy? Could science retain its predictive power when confronted with infinite possibility spaces? Did individual cosmic histories have any significance if they were repeated infinitely many times throughout the larger ensemble? Yet the patterns of renewal and recycling that operated across all observed scales of cosmic evolution suggested that the universe might indeed be governed by principles that transcended individual cosmic histories. Just as biological evolution produced similar solutions to environmental challenges through convergent evolution, cosmic evolution might follow attractors that guided very different universes towards similar endpoint configurations. The emergence of complexity itself might be one such attractor. Despite the apparently random initial conditions produced by quantum fluctuations during inflation, the universe had spontaneously organized itself into hierarchical structures of increasing sophistication. First hydrogen and helium atoms, then stars that forged heavier elements, then planets where complex chemistry could operate, then living systems that could process information and modify their environments. This progression from simplicity to complexity seemed to operate despite the second law of thermodynamics, which demanded that entropy increase over time. The resolution lay in recognizing that the universe was far from thermodynamic equilibrium. The expansion of space and the gravitational instability of matter created free energy that could be harvested by self-organizing systems. But the ultimate fate of complexity remained uncertain. Would the accelerating expansion of space eventually tear apart all organized structures, returning the cosmos to a state of maximum entropy? Or might the universe discover new mechanisms for regenerating order from disorder, extending the reign of complexity indefinitely into the future? The answer might depend on subtle details of dark energy evolution and quantum gravity that remained beyond current observational reach. But the historical precedent was encouraging. At every previous apparent endpoint in cosmic evolution, the Big Bang singularity, the end of inflation, stellar death, galaxy collisions, the universe had discovered new mechanisms for renewal and continued evolution. Perhaps the most profound insight emerging from modern cosmology was that endings were always beginnings in disguise, that apparent terminations invariably reveal themselves as transitions to new phases of cosmic organization. The universe seemed to be eternal, not because it never changed, but because it never stopped changing, cycling through endless transformations while preserving the underlying principles that made complexity and consciousness possible. Our Big Bang, viewed from this perspective, was neither the beginning nor the end of cosmic evolution, but simply the latest chapter in an eternal story of death and rebirth, destruction and creation, chaos and order locked in an endless dance across the infinite expanse of space and time. The silence that began this inquiry was not empty after all. As we reach the end of our journey through the deepest mysteries of cosmic origins, we find ourselves confronting a reality far stranger and more magnificent than the simple story of creation from nothing that dominated human thinking for millennia. The universe before the Big Bang was not a void waiting to be filled, but a realm of such exotic physics that our familiar concepts of space, time, and causation become as inadequate as a child's drawing compared to a photograph. In the laboratories and lecture halls where humanity's greatest minds have wrestled with these questions, a consensus has emerged from the chaos of competing theories. Whether through the quantum bounce of loop cosmology, the brain collisions of string theory, the conformal transitions of cyclic models, or the eternal inflation of the multiverse, virtually every serious attempt to understand cosmic origins points toward the same revolutionary conclusion. Our Big Bang was not the beginning of everything, but merely the beginning of everything we can directly observe. The evidence, while still emerging from the noise of cosmic evolution, tells a consistent story across multiple independent lines of inquiry. The anomalies in the cosmic microwave background, those subtle deviations from perfect randomness that shouldn't exist if inflation had completely erased all traces of pre-existing conditions, whisper of physics operating in realms beyond our current understanding, the patterns of large-scale structure formation, the properties of dark matter, the unexpected characteristics of primordial black holes, all point toward processes that operated before our cosmic expansion began. Most remarkably, these signatures seem to preserve information across what should have been an impenetrable barrier. The Planck epoch, that 10 to the negative 43rd power seconds when classical physics breaks down completely, was not the absolute boundary between knowledge and mystery that physicists had assumed. Instead, it appears to be a phase transition, a moment when one type of physics gave way to another, but where information could still flow from the pre-Big Bang realm into our observable universe. This revelation fundamentally alters humanity's place in the cosmic order. We are not the products of a unique moment of creation, but rather the latest iteration in what may be an eternal process of cosmic evolution. Our universe, with its 100 billion galaxies and its 14 billion years of history, might be just one bubble in an infinite foam of space-time, one note in an eternal symphony of creation and destruction that has no beginning and will have no end. Yet this expanded cosmic perspective, far from diminishing human significance, actually enhances it in profound ways. If our universe is embedded within a larger multiverse, where every possible configuration of matter and energy exists somewhere, then consciousness itself becomes one of the most remarkable phenomena in existence. The ability to ask questions about cosmic origins, to decode the mathematical laws that govern reality, to contemplate our own place in the grand scheme of existence. These capabilities represent something genuinely extraordinary, emerging from the cosmic evolutionary process. Consider the improbable chain of events that led to this moment of understanding. Quantum fluctuations in the pre-Big Bang realm somehow gave rise to the density variations that would eventually become galaxies. Within those galaxies, stars formed and died, forging the heavy elements necessary for rocky planets. On at least one such planet, chemistry became biology, biology became neurology, and neurology became consciousness capable of contemplating its own cosmic origins. The anthropic principle, which initially seemed to reduce cosmology to environmental selection effects, reveals itself instead as pointing towards something profound about the relationship between mind and cosmos. If conscious observers can only exist in universes with very specific properties, then the emergence of consciousness represents a kind of cosmic self-selection, the universe becoming aware of itself through the evolution of complex information processing systems. This perspective suggests that the question, "What was the universe like before the Big Bang?" is not merely an abstract intellectual puzzle, but rather the universe's attempt to understand its own deepest nature through the minds it has evolved. We are not external observers studying cosmic evolution from the outside, but rather participants in that evolution, temporary patterns of organized complexity through which the cosmos examines its own history and contemplates its own future. The mathematical structures that physicists have discovered to describe pre-Big Bang physics, the equations of loop quantum gravity, the higher dimensional geometries of string theory, the conformal transformations of cyclic cosmology, represent more than just human intellectual achievements. They reveal deep patterns in the organization of reality itself, suggesting that mathematical relationships are not merely tools for describing the universe, but actually constitute the fundamental fabric from which physical reality emerges. This insight connects to some of the most profound questions in philosophy and physics. Why do mathematical descriptions of nature work so remarkably well? Why does the universe seem to be organized according to principles of symmetry, conservation, and optimization that human minds find beautiful and elegant? Perhaps the answer is that mathematics and physics are not separate domains, but different aspects of a single underlying reality, where information rather than matter or energy is the most fundamental constituent. If this is true, then the pre-Big Bang realm might best be understood not as a physical space filled with exotic particles and fields, but as a kind of computational substrate, an information processing system capable of generating physical realities through purely mathematical operations. Our universe would be one such computation among infinitely many others, with the Big Bang marking the moment when abstract mathematical relationships began to manifest as concrete physical phenomena. This computational view of cosmic origins offers intriguing possibilities for understanding how information might survive transitions between different cosmic epochs. Just as a computer program can transfer data from one operating system to another through appropriate translation protocols, the mathematical structures governing pre-Big Bang physics might be capable of encoding information in ways that remain accessible to post-Big Bang observers. The circular patterns that Roger Penrose claims to detect in the cosmic microwave background, the correlations predicted by loop quantum cosmology, the statistical anomalies found in large-scale structure surveys, all of these potential signatures might represent different aspects of this information transfer process. The universe might be constantly writing its own history, encoding the memory of previous cosmic cycles in the quantum structure of space-time itself. But perhaps the most profound implication of modern pre-Big Bang cosmology is what it reveals about the nature of time itself. In our everyday experience, time flows from past to future, in a linear sequence, with each moment following inevitably from the previous one. Causation operates through direct physical contact. One event influences another only by sending some form of signal or energy across space. The physics of cosmic origins suggest that this familiar picture of temporal causation breaks down at the most fundamental level. If our Big Bang emerged from internal inflation, then before and after lose their meaning in the larger multiverse where inflation continues forever. If cyclic cosmology is correct, then time becomes circular, with each cycle's end giving rise to the next cycle's beginning. If the universe is a mathematical structure existing timelessly in some abstract space of possibilities, then temporal flow itself might be an emergent illusion, rather than a fundamental feature of reality. These possibilities challenge our deepest intuitions about existence and causation. How can something exist without having been created? How can effects precede their causes? How can the universe bootstrap itself into existence through processes that transcend the normal flow of time? The answers, when they come, will likely require new conceptual frameworks that extend far beyond current human understanding. Just as quantum mechanics forced 20th century physicists to abandon classical notions of particle trajectories and definite properties, 21st century cosmology is pushing us toward even more radical revisions of our fundamental concepts. We may need to abandon the notion that existence requires creation, accepting instead that some aspects of reality are simply eternal, not because they have always existed in time, but because they exist outside of time altogether. We may need to develop new kinds of logic that can handle circular causation and self-reference, where effects can precede their causes and systems can give rise to their own preconditions. Most challenging of all, we may need to accept that the ultimate nature of reality transcends not only human experience, but human comprehensibility. The mathematical structures that seem to underlie physical reality may be describable through equations and computational models, but their deepest significance might forever elude intuitive understanding. Yet this limitation does not diminish the extraordinary achievement represented by our current understanding of cosmic origins. In less than a century, humanity has progressed from viewing the Milky Way as the entire universe to recognizing that our cosmic home might be one bubble among infinitely many in an eternal multiverse. We have moved from treating the Big Bang as an absolute beginning to understanding it as one phase transition in an ongoing cosmic evolution that extends infinitely far into both the past and future. This knowledge comes with both exhilaration and vertigo. The universe revealed by modern cosmology is far grander and more mysterious than anything our ancestors imagined, filled with possibilities that stretch the limits of human comprehension. But it is also a universe where human consciousness represents something genuinely remarkable, perhaps the only way the cosmos has discovered to contemplate its own existence and meaning. The detectors and telescopes that will test these ideas in the coming decades, the next generation of gravitational wave observatories, space-based cosmic microwave background missions, extremely large ground-based telescopes capable of observing the first stars and galaxies, will provide increasingly precise glimpses into the pre-Big Bang realm. Each new measurement will refine our understanding of which theoretical models best describe cosmic origins, potentially revealing aspects of reality that remain completely hidden from current observation. But even as our empirical knowledge advances, the deepest questions about cosmic origins may remain forever open to multiple interpretations. The very success of modern physics in describing reality through mathematical structures raises the meta-question of why mathematics should be so effective in the first place. The anthropic principle, which explains fine-tuning through observer selection effects, inevitably leads to questions about the nature of consciousness and its relationship to physical law. Perhaps this is as it should be. The universe that has evolved conscious observers capable of asking questions about cosmic origins may be the same universe that ensures those questions can never be answered completely. The mystery of existence might be not a problem to be solved, but an inexhaustible source of wonder that drives conscious beings toward ever deeper understanding of their cosmic context. In the end, asking what came before the Big Bang may be less important than recognizing what the question itself reveals about our nature as conscious beings embedded within a cosmos of extraordinary complexity and beauty. We are patterns of organized matter and energy that have become sufficiently complex to contemplate the origin of all patterns, temporary eddies in the flow of cosmic evolution that have achieved the capacity to understand evolution itself. The universe before the Big Bang was not nothing waiting to become something. It was the eternal creative principle that manifests as the endless dance of existence itself. Birth and death, order and chaos, question and mystery, consciousness and cosmos, locked together in a relationship so intimate that asking about one inevitably leads to contemplating the other. Perhaps the question isn't what came before the Big Bang, but whether before exists at all and what that means for the nature of reality itself. In pursuing this question to the limits of human understanding, we may be approaching the edge of a mystery so profound that it can only be lived rather than solved, experienced rather than explained, participated in rather than observed from the outside. The silence that preceded our universe was pregnant with all the possibilities that would eventually unfold as stars, galaxies, planets, life, and consciousness. In contemplating that silence, we complete a cosmic circle. Matter become conscious, consciousness contemplating matter, the universe achieving self-awareness through the very beings it has evolved to ask questions about cosmic origins. This is perhaps the ultimate answer to what existed before the Big Bang, the eternal potential for existence itself, waiting not in time but outside of time, ready to manifest as the endless creativity of cosmic evolution. And we, in asking the question, are both the products and the stagents of that creativity, temporary expressions of the universe's capacity to understand itself through the minds it has brought into being.